He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
Kia ora, and welcome to Elemental, a podcast from RNZ. We are celebrating the International Year of the Periodic Table of the Elements. We being me, Allan Blackman from the Auckland University of Technology.
And me, Alison Ballance. Along the way, as well as some chemistry, we seem to be picking up a bit of Latin and Greek and learning a little history and mythology. Hey, now someone's actually analysed what proportion of the elements are named after different things, such as countries, scientists, a property of the element itself, etc., etc. And it turns out that 8% of them are named after a mythological concept or character.
Oh, very good. I have to say I didn't know that. But that is indeed true of today's element, which is Promethium. And that was named after the Greek Prometheus. And he was a guy who went and stole fire from the gods to give to people. And the gods weren't too thrilled about this, and so in punishment he was tied out on a rock each day for an eagle to feast on his liver, which regrew at night so he could repeat the suffering all over the next day. And I just watched a Black Mirror episode about 2 nights ago which used this exact same concept. So, yeah, nasty.
That's the worst kind of Groundhog Day. Blech. That's a gruesome myth to do with what I actually think is an otherwise unremarkable element.
Yep.
So what has Promethium done to deserve this epic name?
Okay, so as usual, the vital statistics. So elemental symbol PM, atomic number 61, that puts it in the lanthanoids, near the start of those. And it was discovered in 1945. So, if it's unremarkable, it's certainly got an interesting story, I guess. So, it was first proposed in 1902 by the Czech Bohuslav Brauner. And he said that there had to be an element somewhere between neodymium and samarium on the periodic table, because there was a gap there. So that was all very well and good, but it took another 43 years for the element to be isolated because there isn't actually any on the Earth.
Really?
Perhaps I'm probably exaggerating a bit there, but certainly not much. So there really isn't a hell of a lot of Promethium on the planet, and we'll see the reason why if you keep listening.
I'm listening.
Yeah.
Ready.
And everybody else, yes. So they eventually obtained Promethium by looking at the fission products of uranium. And this was in 1945 at the Oak Ridge Lab in Tennessee. And this is a laboratory where they did a lot of the early nuclear work. And they may have discovered it in 1945, but again, there was a war on and all that. So this is one of a handful of elements whose discovery wasn't announced until the end of the war. And in Promethium's case, that was 1947, before it was published. Between those two times, between 1902 and 1945, there have been various claims to the discovery of this element, element 61, and each came with different proposed names depending on where the purported discoverers were. And so these names included Florentium and Illinium, and that was after Florence and Illinois State University, respectively. And then they wanted to call it cyclonium, and then, very good one this, clintonium. And that was actually going to be its name because its ultimate discoverers suggested that one, because the Oak Ridge Labs were known as the Clinton Labs at the time, or they were part of the Oak Ridge Labs, certainly. However, thankfully, a lady by the name of Grace Mary Coriel, and she was the wife of one of the Oak Ridge team, suggested the name Promethium because the name reflects power and peril of nuclear energy, because it symbolises, quote, both the daring and the possible misuse of mankind's intellect.
And that's very true, isn't it, about radioactive elements? So another one of those secret World War II radioactive discoveries that led ultimately to the atomic bomb. Why is it so rare?
Okay, so here is the kicker. All of the isotopes of Promethium are radioactive. Now, that's not necessarily unusual. For example, all of the isotopes of uranium, for example, are radioactive. But yet we have uranium on the planet. The difference with Promethium is that the longest-lived isotope of Promethium, and that's Promethium-145, has got a half-life of only 17.7 years. So, if you do the maths, that means that 99.9% of any sample of Promethium will have disappeared after a total of 177 years. It's basically all gone in that time span. So, obviously, when you consider the fact that the Earth is around about 4.5 billion years old, any promethium that was there at the beginning has long since decayed away. Now, that's not to say that there's absolutely no promethium on the planet. So small amounts of promethium are formed from the natural fission of uranium, or there's a particular neodymium isotope that can react with cosmic rays to form a promethium isotope. And so roughly speaking, it's thought that there's about 500 grams or so on Earth at any time. Why is this? Why are all of the isotopes of promethium radioactive, and thereby making promethium so unabundant, for want of a better word, on Earth? So the question I'm asking really is, why are there no stable isotopes of atoms containing 61 protons? And it's not the only one. As we will see, there's another element that contains 43 protons, which also doesn't exist on Earth. We'll get to that. I won't tell you which one that is. You'll have to wait for the episode. But the reason for the instability of promethium is, here we go, it's a thing called the Matauch isobar rule.
Whoop, whoop, pull up. Isobar. Now, I think of an isobar in terms of weather maps. So, an isobar being a line of constant pressure, like a contour line on a map, except it's on a weather map. So what does it mean chemically?
Okay, so chemically it means something a little bit different. So isobars are two nuclides that have the same mass number.
And a nuclide, when it's at home, is what?
That's a brilliant definition. You define one thing with a word that you don't know the meaning of, So a nuclide, very, very simply put, is to nuclear physicists what an isotope is to a chemist. So nuclides have got the same mass number, isotopes have got the same atomic number. So if you can sort of get your head around that, remember the mass number is the sum of the number of protons and neutrons in the nucleus. So, while you're thinking about that, the Matauch isobar...
You can probably hear my brain from here. Tick, 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 tick.
So, the Matauch isobar rule says that if you've got isotopes of two atoms that are neighbours on the periodic table and they have the same mass number, then one of those isotopes has to be radioactive. So basically that means that if the two elements on either side of your element in question have got lots and lots of stable isotopes, then the one in the middle is going to be in trouble. So, and this is what happens in the case of element 61, promethium. So its neighbours are neodymium and samarium, and they appear to have a stable isotope for each mass number that they share with promethium. So I guess this is just one of the wonderful accidents in the periodic table, that element 61 is surrounded by two elements who have lots and lots of stable isotopes, and likewise element 43, the same sort of thing. So that's why there's very, very little, if any, of elements 61 and 43 on the planet Earth.
How weird is that? I'm terribly sorry, but your neighbour with whom you share a mass number, well, they bagged the non-radioactive role first, so... Well, you'll just have to be radioactive, won't you?
Yep, indeed. It is strange, and the explanation I just gave is not really so much an explanation, it's more just a rationalisation when you think about it, but we're not going deeper than that. Okay?
No, we've gone down enough rabbit holes, thank you.
So, now the one really remarkable fact about promethium is the fact that its spectral signature has been seen in a number of stars. So we can actually see the fact that promethium exists in stars. And so because of the fact that its half-life is so short, this means that it must be being produced in significant quantities for us to be able to detect it, and also that it must be being produced on the surface of the star, because atoms take a very, very, very long time to get from the interior to the surface of a star. We're talking sort of thousands, millions of years. And so any promethium that's formed in the interior would decay away before getting to the surface. So really nobody knows what's going on about all this. And of course, realizing that light from those stars has taken, thousands and thousands and millions of light years to get to us, then this was all happening in the deep, distant past. So, yeah.
Gracious, you've gone all astronomical on me. But back here on Earth, Alan, back to Earth,
Yeah.
I'm guessing there's not a huge number of uses for it.
No. Just the mere fact that all of its isotopes are radioactive, that sort of cuts out a lot of its uses, and the fact that it's got a very, very short half-life, so there really ain't a heck of a lot of it around. So it has been used in some very, very specialised batteries, and it also has been used to measure the thickness of steel using its beta decay, but really that's about it.
And interesting fact?
Well, okay, I can go with this one. So Promethium-147, one of the isotopes, has been used in luminous paints. So its beta emissions cause a phosphor to produce light. And in fact, some of the switches in the Apollo lunar modules were illuminated this way.
Well, that's a nice thought, these little glowing switches on the modules, which I have to say, that Apollo mission has kept cropping up again and again, like in thruster nozzles and luminous switches, through this podcast series. And that's kind of a nice thing, because it's 50 years since the Apollo mission landed us on the moon, way back when. So how topical are we?
Oh, very much so. And because it's 50 years, I guess then the Promethium in those lunar modules will have at least pretty much half a decade away anyway. It was used in the Apollo lunar modules probably because it's safer than radium, which we are coming to, but it's got a half-life of around about 2.5 years, so pretty short half-life. They're not going to stay bright for very long, so Promethium has now fallen out of favour for these sorts of things, and we use radioluminescent materials now based on tritium, which does have a longer half-life.
And just like this podcast, these new ones can stay illuminated for significantly long periods of time. Elemental, casting a bright light on chemistry on a podcast app near you. And if you haven't already subscribed, you'll find us on most podcast apps as RNZ Elemental. Google Podcasts, Apple Podcasts, Spotify. We're free.
Of course, you can also listen to us online at rnz.co.nz/chemistry. We are back next time with Protactinium. But until then, it's cheerio from me, Allan Blackman.
And me, Alison Ballance. Mate wa.